Alrighty, today we're going to learn about impulse and momentum. So the first thing we need to talk about is what is impulse. So impulse is force times time. And if you want to think about impulse as if you want to change the velocity of something, you need to apply an impulse. So you can apply an impulse either by pushing on something with a big force or a small force. But you also need to push on it for a certain amount of time. And so, if you want to apply a bigger impulse to get it to change velocity more, you can apply a bigger force or you can push on it for more time. So, think about if you are in a grocery store and you want to get your grocery cart moving really fast, but it's really heavy, then you have a couple options. You can push on your cart really hard for a short amount of time, or you can push on your cart with a smaller force for more time to get it to speed up the same amount. You can also think about it as slowing down. If you are in a car and you can see a red light coming up, oftentimes people will let off on the accelerator and start slowing down. So you can slow down over more time, but with a smaller force. Uh, or if you all of a sudden notice that the light just turned red, you didn't notice it, you slam on the brakes, you apply a big force in a small amount of time. That would also give you that impulse to stop. But how are we going to figure out how much velocity it changes? Well, the first thing we need to learn about is momentum. Momentum is kind of like how much motion oomph something has. And what has and so one way to explain this is think about what has more momentum, an elephant on a scooter going slow or an identical elephant on a scooter going fast. Think about it. Yeah, so the elephant going faster is going to have more motion oomph or momentum. Another scenario I want you to think about is I have an elephant and a mouse riding their scooters together at exactly the same speed. And who is going to have more momentum? The elephant, which has a much bigger mass, or the mouse with a much smaller mass, but they're both going at the same velocity. Good. So the elephant is going to have more momentum because it has more mass. So if you want to know how to calculate momentum, momentum is equal to mass times velocity. And the letter for momentum is a lowercase p. You can't use an uppercase p because uppercase p is going to be power. So you're going to want to get in the habit of using a lowercase p for momentum. To find total momentum of a system, for example, if there's multiple different objects, all you need to do is add their momentums together. So just like when we were doing moment of inertia and we just added the moments of inertia of all the pieces together, we can add the momentums together of everything. So if I want to know the momentum of a car and the person in the car, I can just add the momentum of the car plus the momentum of the person to get my total momentum. So my question then is, how are momentum and impulse related to each other? So I'm going to start here at the top. F equals ma. We are familiar with that. We also know acceleration is equal to your change in velocity over your change in time. So if we combine these two equations together, we have F equals ma, but instead of the a, I'm going to use the change in velocity over change in time. In this step, I just take and move time to the other side by multiplying times your change in time to both sides. And I get my impulse is equal to my change in momentum. Now, the most important thing here that I need to emphasize is that it is the change in momentum. It is not the actual momentum. So impulse being equal to your change in momentum is important because when you are thinking about, let's say you're on the freeway, you're already driving 65 miles per hour, and you want to get going a little bit faster, You don't have to apply a really ginormous force to speed up to 70 miles per hour. You just need to apply enough force over enough time to speed up by 5 miles per hour. So when you're doing this, be really sure that you're remembering that it's your change in momentum that's equal to your impulse. So my change in momentum is equal to impulse. You're really never going to see J used as impulse. Most of the time, you're going to see it as just force times time. So if I think about my change in momentum, that's the same as my change in mass times velocity, and that'll be equal to my force times time. But for example, if I want to make a bowling ball speed up and I need to push on that bowling ball, my mass of my bowling ball is not going to change. So in reality, when I say change in momentum, what I'm really saying is it's my mass times my change in velocity. And that's going to be what's equal to force times time. Now, you need to know what this looks like on your equation sheet and why I'm emphasizing the importance of change in momentum. So on your equation sheet, these are the two lines that are right next to each other. You have momentum is equal to mass times velocity, and you have change in momentum is equal to force times your change in time. And oftentimes I will see students just take this equation, go mass times velocity, and plop it in for this P, instead of writing mass times your change in velocity. And so that's the number one mistake that I see here, is that students just take MV and put it in here instead of doing mass times your change in velocity. So just be really careful with that. All right, so what is the momentum of a 300 Newton gorilla running at 4.9 meters per second? Go ahead and pause this and calculate it. All right, so now that you've calculated, I want to point out this is a 300 Newton gorilla, not a 300 kilogram gorilla. If you just realize you did that wrong, go ahead and pause and do it again. Otherwise, I'm going to show you the answer. So momentum is equal to mass times velocity. Unfortunately, this is the gravitational force or weight of my gorilla. So if you remember, Fg is equal to your mass times g. And so this 300 newtons is your gravitational force. G is 9.8. So you'll end up with 300 is equal to mass times 9.8. So you divide both sides by 9.8. And then this part here is what is getting plugged in right here. Then you multiply that times your velocity and you get 150. So now get this straight. Impulse and momentum are both vector quantities. So you need to remember that both impulse and momentum are vectors, which mean that they have both magnitude or size and direction. So it makes sense because when we're talking about momentum, it's mass times velocity, and velocity definitely has a magnitude and direction. It matters, am I going to the left or am I going to the right? It matters how big that velocity is. Now, the same thing applies for impulse. I can push to the right or I can push to the left. And that's going to make a big difference in terms of what happens to my object. So you need to pay attention to which direction it's going. If your force is going one way and your velocity is the opposite direction, it's going to slow down. If they're both in the same direction, then it's going to speed up. So I'm going to go over a couple things from the beginning of the semester. A quick reminder, here is your position is equal to 1/2 times my acceleration times time squared, plus my starting velocity times time, plus my starting position. And when our starting position was 0 and our acceleration was 0, then these two terms went away, and we're just left with my change in position is equal to velocity times time. So what that means then is when we had a velocity versus time graph, the area of that graph was equal to my displacement, or how far I went. Now, this works great if you're going at a constant velocity, because that area is a rectangle. So you can just do velocity times time. But
the reason why I bring this up is it does not work if you're speeding up or slowing down. So for example, if you're speeding up, now that graph is going to look like a triangle. So now I have velocity versus time, but now the area is not a rectangle. So if I did 50 times 5, I would get the wrong answer because I was not going 50 meters per second for the whole 5 seconds. So what I need to do instead is find the area of a triangle. And the area of a triangle is 1/2 base times height, or base times height divided by 2. And so that area is what matters. And so this equation, position is equal to velocity times time, doesn't work because of that acceleration. So be careful, don't fall into that trap. But if you'll notice, this is very similar in format to our idea that impulse is equal to force times time. So let's look at that. So if I have then instead a graph that is impulse is equal to force times time, then the same way that I did velocity times time before, I can do force times time to get the area underneath this to be equal to my impulse. But I can't just multiply my maximum force times time because this is not a rectangle. And in fact, this is usually what the force versus time graph looks like. So you'll need to just approximate the area underneath. Or what you'll see happen very often in these problems is it'll either give you your average force, which you would be able to multiply times time, or it'll do this as a triangle to approximate it, in which case then you just do 1/2 base times height, and it doesn't matter if it's an isosceles triangle or a right triangle. You'll still be able to do 1/2 base times height to get that area. So, because impulse is equal to your change in momentum, you can also say that the area under a force versus time graph is equal to the change in momentum. All right, let's look at an example. So here I have a baseball player hitting a bat, or sorry, a baseball player hitting a ball with a bat. And as the ball starts being in contact with the bat, you'll notice that the ball itself is getting compressed, it's getting squished. And then up here at the top is when you're going to have your maximum force. That's when the ball is at its maximum squishedness. And then as it expands and gets to be a normal ball shape, again, the force decreases. So this is what the graph actually looks like. You'll also notice in this GIF that the bat itself changes shape as the ball hits it. Kind of cool. So we have a couple different ways of thinking about this. So if I have a car that's going to crash and stop, and let's say it was going the same initial velocity, and it's going to stop, and both cars are identical, so they have the same mass, that means they have the same momentum. And if I stop, then I need to have the same zero ending momentum. So if that's true, then I'm going to have the same change in momentum and therefore the same impulse, because change in momentum is equal to impulse. So what I can do is I can either apply a smaller force over more time to get this car to stop, or I can apply a bigger force over a shorter amount of time to make my car stop. Both of these, the area is the same. My impulse is the same. My change in momentum is the same. The difference is that the maximum force is less, which is good because if you don't want to get hurt, you want a smaller force exerted on you. So at this point, I'd like you to take a break. I want you to think about what is momentum, what is impulse, how are momentum and impulse related, what is the equation for this on your equation sheet, what does the area under a velocity versus time graph tell you, and what does the area under a force versus time graph tell you. So take a break. When you're ready to resume, go ahead and resume. All right, so a golfer is told to follow through with his swing. This keeps the ball in contact with the club over a longer time, increasing the impulse and thereby increasing the velocity. He can apply a constant force during his entire swing. So the greater the time of contact, the greater the momentum change of the ball. So here we have force times time is equal to my change in momentum. So if that force is the same the whole time, then if I apply a bigger amount of time, or if I apply the force for a bigger amount of time, I will have a bigger change in momentum, which means that the velocity of the ball will be bigger when it leaves the golf club. Another example of this is in boxing. Boxers can ride with the punch. And what that means is if you're getting punched in the face like this, you can get punched and kind of keep going as you're getting smacked, so that way you have a smaller force over a longer amount of time, so that way it doesn't hurt your face as much. Or you can lean into the punch. So if here comes the punch and I lean into it, now I'm going to have a smaller amount of time that I'm in contact with the fist, and therefore a much bigger force. This one, it makes obvious sense that this is going to hurt more than if you follow through with the punch. So this one is another boxing example. Here we have the puncher hits with a constant force and wants to increase the time of contact, increasing the impulse and thereby change of momentum of his opponent's head. So if you want your opponent's head to be moving away from you really fast, you need to push it for more time. So here's where you're going to want the follow through. Just like the golf example, you're going to want to follow through with your punch in boxing. So why would a padded dashboard be better in a car crash? Go ahead and pause this, think about it, and then resume. So a padded dashboard is going to do the same thing as the haystack. You're going to have a longer time of impact, which means that your force is going to be smaller. It's not that there's going to be a difference in momentum. The change in momentum will be exactly the same. The difference is that you're going to have a smaller force over a greater amount of time to experience the same impulse and change in momentum. So it'll hurt less. So now we're going to move on to the law of conservation of momentum. Now, what this says is that the momentum before needs to be equal to the momentum afterwards. And the symbol for momentum is P. So we have isolated systems and non-isolated systems. So when you have an isolated system, this is where you're going to have conservation of momentum. So all of the objects that are hitting each other are all in your system. So for example, you have two cars that are driving and they crash into each other. You're going to have conservation of momentum. If instead you have something coming from outside of your system and hitting it, for example, like a baseball bat hitting a baseball, then it's not going to be an isolated system because you have an external force acting on your system. So if momentum is conserved, there are three things. There is no external net force acting on the system. The velocity of the center of mass of the system remains unchanged by a collision or explosion, and the momentum along each axis is also conserved. So let's do an example. This is an example of a bicyclist. Bike and rider is 80 kilograms, and they are riding at a constant velocity of 5 meters per second. When he is overtaken by a flying mass of silly putty of 30 kilograms, traveling at 15 meters per second. And I want you to calculate the final velocity of the resultant mess. All right, so the first thing I want to teach you guys is how to do a bar graph for momentum. So I'm going to think about the momentum of before and the momentum of after. So before, I have my bike moving. So my bike is going to have some amount of momentum here. And so that's the momentum of my bike. And then my putty also has momentum. And so we're going to say my putty has this much momentum beforehand. And because I know the momentum before needs to be equal to the momentum afterwards, I know that this amount added together needs to be equal to the same amount on the right hand side. So let's say after the collision, I know they're stuck together. And because they're stuck together, they're going to have the same velocity after they get stuck together. So because the bike has a bigger mass, I'm going to expect my bike to have a bigger momentum because it has the same velocity but a bigger mass. So just like the elephant and the mouse on the scooters from the beginning of this lesson. Okay, so here we go. So if I add these two together, and I could even go plus, and I need these to be equal to this side, and I can do plus over here. And then I can think of this as momentum of the bike and momentum of the putty. So let me just put in mass times velocity for each of these.
All right, so now I have the mass times velocity of the bike, mass times velocity of the putty, and that'll be before they collide. And then I have the mass of the bike times the velocity of the bike here, and the mass of my putty times velocity of my putty. So all I would need to do is plug these numbers in, and I can solve then for my velocity of my putty. All right, so I'm going to go ahead and type this out instead. All right, so I have my momentum before is equal to my momentum afterwards. So I had the bike and the putty for each, and I put in the mass of the bike and the mass of the putty. Then I could put in the numbers. So the bike plus ride area is 80 kilograms. They're originally traveling at 5 meters per second. The mass of my putty is 30 kilograms, and it was originally traveling at 5 meters per second. Then I have the mass of each over here, and then the velocity when they're stuck together. Because originally I had the velocity of the bike and the velocity of the putty, but once they're stuck together, in order for them to be moving together, they need to have the same velocity. So I just called it velocity combo. And instead of writing out combo every time, I just shortened it to V. And then I solved. I added the 400 and the 450 together, and then 80V plus 30V is just 110V. You could think of it as adding x's. It behaves the same way. Divide both sides by 110, and you get 7.73 meters per second as your velocity once they are stuck together. Now, the other way to think about this is you can think of it as the momentum of the bike plus the momentum of the putty is equal to the momentum of everything. Well, the momentum of everything is going to be the mass of everything added together times the velocity of everything when it's going together. And so either way you do it is totally fine. This way is you just have to be careful when you're doing impulse as well. So just heads up. All right, so here is an example of a firecracker. A firecracker at rest explodes. A 1 gram particle flies off at 30 meters per second, and a 3 gram mass flies off in the opposite direction. So the way you do this on one of the graphs is you have one of them going in the positive direction and the other going in the negative direction. So both pieces started from rest, which means that their momentum is zero, because whatever their mass is times the velocity of zero is going to give you a momentum of zero. And then have that equal to the momentum of one going one way times the momentum or plus the momentum of the other going the opposite direction. So I'm going to go ahead and put in the plus signs here. And then I'm going to put in mass times velocity. And then I'm going to substitute in the numbers and solve for the velocity of the 3 gram piece. So just do 1 times 30, subtract 30 from both sides, and I get a velocity of negative 10 meters per second, which makes perfect sense because I do expect it to be going in the opposite direction as the first one. And I said the first one was moving in the positive direction. So a 45 kilogram girl standing at rest on a frictionless frozen pond catches a 5 kilogram ball moving with a velocity of 10 meters per second. What is her resulting velocity? I want you to pause this, do it, and then come back. All right, so your answer should be 1 meter per second. For the momentum of the ball beforehand, that's just my mass times velocity of the ball. The girl's not moving, so her momentum will be zero.
And then afterwards, they are going at the same velocity. So I did the thing where I just added the masses together and I got 1 meter per second. So here's another example. Here I have a cannon shooting a cannonball. Before the cannon is shot, the momentum of the cannon and the cannonball is 0 because neither one is moving. But once I shoot it, I need to still have the same momentum. So that means the momentum of the bullet going forwards is going to be the same as the momentum of the cannon going backwards. So that way I have the same momentum before the explosion and after the explosion. So here's a little cartoon. You load up a bowling ball into your cannon, you shoot the cannon goes backwards, and the bowling ball went forwards, but only a tiny little bit. So, strictly speaking, when a gun is fired, compared with the momentum of the recoiling gun, the opposite momentum of the bullet is it less, more, or the same? Think about it. And a recoil, for those of you that don't know, is if you shoot a gun, when you shoot the gun, the bullet goes that way. And so then the gun needs to go backwards the same way as the cannon example just did. So a recoil is when you shoot it, the bullet goes forward, your gun's going to go backwards because of conservation of momentum. So you probably said that these are going to be the same, but I want you to think real life. In real life, it's going to be less because the bullet comes out of the barrel, yes, but there's also gas that comes out of the barrel of the gun. And it's not an insignificant amount of momentum from the gas because the gas in like the air does have mass and it is going very fast. So the momentum of the recoiling gun is actually going to be equal to the momentum of the bullet plus the momentum of the gases. And that is why you can get really hurt from a gun, even if there's no bullet, because of the gases that come out of the gun. So there are two kinds of collisions that we are going to talk about today, inelastic collisions and elastic collisions. I want you to first notice that regardless of what kind of collision it is, inelastic collisions, momentum is conserved. Elastic collisions, momentum is conserved in all three of these. So all three momentum is conserved. And in inelastic collisions, it's when two objects stick together or they were stuck together and now they're not, like an explosion. Kind of like the firecracker example that we already did. Then we have perfectly elastic collisions. This is when two objects bounce off of each other like billiard balls, and no energy is lost. So this is perfectly elastic. You have things bounce off each other and energy is also conserved. But what's going to happen more often than that is not perfectly elastic collisions, where you have two objects bounce off of each other, but some energy is lost. And a good example of this is a normal car crash where you have two cars bounce off of each other, but you still lose some energy. Or bumper cars. You have two bumper cars bounce off of each other. You're going to have conservation of momentum, but not conservation of energy. All right. So billiard ball collisions approach being perfectly elastic. They're not perfect, but a lot of times in physics, we assume that they are. So here we have they collide head on. This is a really good example of nearly perfect. You'll notice that one ball stops and the other one starts moving. And this one over here is not perfectly elastic. What's going to happen over here is the first ball comes in and then it keeps going. And in both of these, you're going to have conservation of momentum. So here they have the same mass, so one stops, the other one keeps going at the same speed. This one, the yellow one, comes in faster and some of the momentum stays on the yellow one, but most of it gets transferred to the red one. So you can tell that they both have the same momentum together before and after. So momentum is going to be conserved in both kinds of elastic collisions. So, two possibilities for the collision. They can collide head on in a perfectly elastic situation. One of them is going to stop and the other one will keep going. Or you could also have them hit at an angle. And if this happens, what's cool about this is you're actually going to notice that they go off 90 degrees to each other. All right, and the last thing of the day, we have an example. A Mack truck or a semi truck is hauling down the highway at 30 meters per second. A mutant suicidal mosquito with a massive 0.10 kilogram plans to collide with the truck head on. How fast must the little guy fly in order to stop the truck dead in its tracks? Go ahead and pause this and calculate it, and then resume. All right, so I have the mosquito and the truck. And so the momentum of the mosquito plus the momentum of the truck is going to need to add together to be equal to 0 because they are going to collide. When I plug in the numbers, I get 0.1 times my velocity is equal to, and then this is negative because of this being a negative 30 meters per second. So I said the velocity of the mosquito is positive, then the velocity of the semi-truck is negative. And so that is going to give me a velocity of the mosquito of 6 million meters per second. Let me know if you have any questions about momentum and impulse. I'm happy to help. Take care.